Hey everybody, and welcome to Chapter 4. So we are talking about Chapter 4, which is all about z-scores and the normal distribution. Okay, so this is quite a chapter. The reason why I say it's quite a chapter is because this is a big turning point in our class. It's one of the most important chapters that we're going to be dealing with all semester. I think this chapter, and then I think it's maybe Chapter 7, are perhaps the most important chapters we're going to cover all semester. And I'm putting all that importance on this because I think for a lot of us, we might need a little bit of extra time with this content and with this chapter. So don't be afraid to rewatch an example if you feel a little bit uncertain about how to do things. Because for some of you, this will be the first time you've learned about this kind of stuff, which is fine because the previous 3 chapters, I think I would probably bet many of you had some exposure to content like that before. This might be where we go into completely new waters. So we're going to be talking about the normal distribution, and we're going to be talking about z-scores. The format of this chapter, I'm going to record 3 videos. The first is going to cover the theoretics of normal distributions, z-scores, what they are conceptually. The second video is going to be kind of like how to do that in practice, like how to apply that information. And the third video is essentially how to go from start to finish with a brand new example if you're working it out by hand. So let's get into it. So I want to start by talking about IQ scores. And IQ scores are obviously controversial because IQ testing, as with lots of standardized testing, there's a lot of reasons to not like IQ scores. But one of the reasons why I really like IQ is because it is a normal distribution. The way they calculate these, the companies that maintain IQ scores, they always make sure that each generation we have a normal distribution. So what does that mean? Basically, if you look at this distribution of these scores, it is symmetrical. In other words, it is not positively skewed or negatively skewed. And we've talked about those concepts in previous chapters. But IQ score always has a mean of 100. And so it has a mean of 100, so we always know where the center of that data are. But we also know that from the construction of this distribution, there are certain things for us to pay attention to. The first piece is going to be this idea of 68%. This is a concept that's going to come up all throughout this chapter, this idea of 68%. Basically what this means is that 68% of the data is going to fall within these boundaries right here. In other words, 68% of our population is going to fall within an IQ score of 85 to 115. So 68% of everyone is there. If we expand that range out further, so from 70 to 115, or sorry, my bad, from 70 to 130, now we're looking at 95% of all of our data is going to fall there. In other words, it's very rare to find someone that has an IQ less than 70 or an IQ above 130. How rare? Basically, it means that the top 2.5% of our population or the lower 2.5% of our population. And that's how all IQ scores are. They all follow this distribution. So this is important because, if you were to say, hey, I have an IQ of 108, is that good? Basically, we could look and say, like, okay, well, it's between 85 and 115, so you're within, 68% of the population, so it's not that different. It doesn't deviate that much from the mean here. So this concept is going to underlie so much of our understanding of inferential statistics. Once we start doing testing, like analyses, they're all going to come back to this idea. So keep that in mind as we move forward and as we look at other examples, that this is what we are all kind of working with, this idea of a normal distribution. So when we have a normal distribution, most of the values in our data set are going to be somewhere right here in the center, right? Because the higher we are on the y-axis basically means that we have more observations. Lower on the y-axis means we have fewer observations. So we have few observations in these tails and lots of observations in the middle. And so because it's symmetric like that, means that as we move away from the center, we are just as likely going to get low observations as we are high observations. So this is sometimes called the bell curve as well, or a bell shape, because it is shaped like a bell. And most data sets that we're going to be working with this semester, we are going to assume that they are going to use a normal distribution. But if we're thinking about in the real world, some other examples of normally distributed data are IQ scores, shoe size and height and birth weight. So shoe size and height, those are things that we don't have any control over, right? And so if you look at, in America, we have some folks that are quite short, some folks that are quite tall, but for the most part, most of us are going to be somewhere between, 5'2", 5'1", and 6 foot. 6'1" or something like that. So most of us are there in that, and there's a few people on either extremes that are shorter than that or higher than that. For real estate, we see the same thing, that most real estate in different neighborhoods are going to follow a normally distributed data curve. If you're rolling 2 dice and trying to calculate the scores, that's going to follow a normal distribution, and sometimes student exam scores follow this too, where we can imagine, an exam where over here we have 100 and over here we have 0, that many people are going to be scoring 70 or whatever, and as we move away in either direction, we have some people make 60, some people make 90. This is not to scale, by the way. And basically what this means is that most people get about 70 or fall somewhere between 60 and 90. It's much rarer for people to fall over in the curves below 60 or above 90. Alright, so there are 7 important features for us to keep in mind as we talk about normally distributed data. So before, whenever you're taking the theory quiz for this chapter, this will probably come up. So the 7 features, the hallmarks, the characteristics of a normal curve. The first is that they are symmetric around their mean, which we just talked about, right? So it's basically symmetrical. The second feature is that the mean, the median, and the mode are the same. In chapter 3, when we're talking about skewness, and in chapter 2, we mentioned that the mean, the median, and mode might be different for your data, and if they are, that usually means that there is some skewness going on. If it is a symmetric data set, there is no skewness, so the mean, the median, and the mode are going to be the same. The area of the curve under the curve is 1.0. In other words, all of our data are going to fall under this curve somewhere. The denser is denser in the center and less dense in the tails. So we have most observations here in the center, fewer observation in the tails. Is defined by 2 parameters. So in order for us to map out this data, we need to know the central tendency and the dispersion. In other words, we need to know the mean and the standard deviation. Almost always. Very, very rare for me to ask for the median and the standard deviation. It's almost always going to be the mean and the standard deviation. And then the final 2 hallmarks is that 68% of the data is within 1 standard deviation of the mean, and 95% of the data are within 2 standard deviations of the mean. And when I say within 1, I mean within plus or minus 1 of the mean. So, 1 standard deviation above and below, and that would be 68% of the data are going to fall here. And then within 2, 95% are going to fall within either 2 above or 2 below the mean. So again, talking about IQ scores, we have a mean of 100 and a standard deviation of 15, and so that's how we know that it's exceedingly rare for people to be above 130 or below 70, because what that's saying is that that's 2 standard deviations above the mean, and that is quite unlikely, or 2 standard deviations below the mean, which is also quite unlikely. So each normal distribution is going to have those 2 parameters, where we have the mean and we have the standard deviation. So that's why I emphasized last chapter why it was so important to be good at calculating the standard deviation, because this is an idea that's going to come up and stay with us throughout this semester. So, two important ideas. One is that not every distribution has a mean of 100 or a standard deviation of 15, right? So if we look at this is a great example of a normal distribution, but it's not the only example of a normal distribution. This does not have to be 100. You can easily imagine if I were to shift all of this down to 85, if 85 were the mean, then it would just look something like this. Right? So we don't necessarily need the mean to be 100 or the standard deviation to be 15. We can play around with those parameters, and that's okay. For different scales, we're going to see that our means can be wildly different. So that doesn't mean that it's impossible for us to compare distributions. So if we had an IQ scale, which has a mean of 100, and we had those exam scores, which had a mean of 70, and a standard deviation of 10, we can actually compare them. We have formulas that will allow us to compare those two scales to look at, for example, if we know somebody's IQ, we might be able to predict their exam score if we think those two measures are related. So let's talk a little bit about standard deviations and a little bit more. It's not sorry, not standard deviation. The standard normal distribution. So the normal distribution is sometimes called the standard normal distribution. The standard normal distribution is essentially whenever we convert a scale. Oop, I don't know if you saw that. I just tossed my pen, my magic stylus, and because as you can see it's super dark in here, I don't actually see where I dropped this. So, you know, most TV shows are able to edit out the bloopers, but you get them for free. So in trying to compare scales, one common way to do that is to refer to a standard normal distribution. A standard normal distribution is, instead of talking about individual units of measure, we're going to convert all the different measurements down to a z-score. You can think of a z-score as a standardized score. And this standardized score is going to have a 0 for the mean and a 1.0 for a standard deviation. So, basically what this means is that for using a standard normal distribution, we're taking something like IQ. And IQ, as we remember, has a mean of 100. And we're going to convert that to a standard normal distribution, which looks just the same, has the same properties, but has a 0 for a mean and a 1 for a standard deviation, which leads us to something like this. So instead of having 115 and 130 and 85 and 70, you know, because the standard deviation was 15 here, we're going to convert the mean to be 0. We're centering it on 0, and then we're turning the standard deviation into 1. So that's the standard normal distribution. We're going to be using that a lot when we're standardizing data, so that we can compare across different kinds of scales. But we're going to use this a lot. So this is going to be an old friend. So if it doesn't feel right, you know, and you've watched this video and it still is not making sense, feel free to email me so we can talk about it, because this is not one of those things I want you to get lost on. All right. Z-scores are calculated once you know your population parameters. So here's what I mean by that. That a z-score is a standardized score. It's going to let you know if you are able to put every scale on a universal size template so that you can compare things like exam scores and IQ scores and height and birth weight and shoe size and depression score and GPA and family earned income. You can compare all of these things by putting them in this standardized score, by finding the z-score here. And so if you want to find the z-score for any value, the way that you're going to do that, because what that would do is it allows you to know exactly how much above or below the mean your observation is. So if, and you know, by way of an example, let's say that I want to know if I have an IQ of 110, just how good is that? compared to the rest of the population. How good is a 110? The way that we would find that is to find the z-score, which what we would do is we would put our score, so we'd put 110 here for x, and then we're going to put in the population parameters here. We already know what those are, 100 for the mean and 15 for sigma, for standard deviation. And we already know that just because we were looking at those examples. And this would give us something along the lines of, what, 10 over 15? And so the z-score for that would be 10 over 15. So if we were looking at 100 then, what this means then is, like, if we put in 100 here, it's going to change this up a little bit, right? 100 minus 100 is going to give me a 0. 0 divided by 15 is still 0, which means I have a z-score of 0. What does that mean? That means that 100 has a z-score of 0. In other words, it is 0 standard deviations away from the mean. In other words, it is right there smack dab on the mean. So if we plug in another example now, so I'm going to erase that, and we plug in 85, I'm going to put in 85 here. 85 minus 100 is negative 15. That gives me negative 15 over 15, which is negative 1. So z-score of negative 1. How do we interpret that? Basically it means that this score is 1 standard deviation below the mean. So if you see a z-score of 3, it means that it is 3 standard deviations above the mean. If you see one that is negative 2.5, it means that that observation, that data point, is negative 2.5 standard deviations below the mean. If we wanted to calculate 122, how do we do that? We just throw in 122 here. So it's going to be 122 subtracted by 100, which is going to give us 22, which is going to give us something pretty close to 1.5, I believe. I can break out my calculator and find that out. 22 divided by 15 is 1.46, which means that 122 is almost 1.5 standard deviations above the mean. So we would know that that was pretty good. Alright, so I am, I'm going to cut the video here and then resume the rest of the video to cover the remaining parts of the chapter because we're about at the halfway point. So I will see you on the other side. Thanks for tuning in.